half of what we need here. Let me introduce the hardware devices group. Barry Brumitt is not here today. He claims he had a prior engagement at a conference on the East Coast and won't be here. Gary Starkweather led me to believe he wouldn't be here and then came, which I'm delighted that Gary's here. Mike Sinclair also led me to believe that he wouldn't be here, and he's actually here, which is great. And I couldn't skate out on this, so I'm actually here, plan to be here, and I'll do all the talking, which means that you're getting all of this secondhand. We are a small group. We've been here for I've been here for 4.5 years, and Gary's been here for 5 years, and we've all been here about the same amount of time. We're just getting off the ground still in that 4.5-year period. But let me talk to you about what we're doing and why we're doing it. Here are the people in the group. Mike Sinclair over here is our MEMS sensors multimedia UI expert. Gary Starkweather is can think of more different ways to drive a display than anybody I know. And Gary's also very keen on the UI aspects of large displays and has been doing a lot of work in that area. Barry Brumitt has just joined the group. He is interested in ubiquitous / invisible / location-based computing, and as am I. And I'm a half-time member of the group, which means I don't get to have nearly as much fun as the other three guys. My interest is in graphics processors, as well as personal area networks, which are a component of ubiquitous / invisible computing. Now, this is all well and good, but it raises the question of why in the world would Microsoft have a hardware research organization? And I may not answer that successfully in this talk, but at least I can gloss it over with a lot of neat stuff, which is reason enough to have a hardware devices group. This is the question I raise inside the company: is when was the last time? Actually, this first question is a bad one. That's right. Yeah. Yes, we always write software for non-existent hardware, but you know the hardware has to exist sooner or later, and it's better it exists sooner, so we can get some kind of sanity check. Traditionally, hardware has led software. That we get these new capabilities, and then we take advantage of it. We could be a reactive company. That is, we wait for this stuff to become available, and then we say, okay, we'll take advantage of it. It's better to be a proactive company, at least from the research standpoint, and that's exactly what we're trying to accomplish with a hardware devices group. Those areas which have an impact on the Microsoft products are pretty obvious. Displays is getting a lot of attention right now in the product group, especially multi-mon or large monitor displays. Memory, especially low-power non-volatile RAM, something we don't have currently, is getting a lot of attention in the product groups. It's something we desperately need in things like tablet or just run-of-the-mill desktop computing. Interconnect, of course, wireless, wide area networks, local area networks, both wireless and wired, have received huge amounts of attention, but personal area networks, which is something you need for untethered computing, is something that has received very little attention, and we're trying to put some work into that. And then sensors, of course, sensors either for user state or machine state, and we're focused on user state, are important as well. These actually matter. They actually matter in our business. And then our catch-all statement at the end is just don't bet against the hardware, which is another way of saying if you're going to get blindsided, you're likely to get blindsided by hardware changes, and we'd rather not be. So staying abreast of what's going on in the business is extremely important. Now, we don't do everything. You don't see a big IC fab down the hall. I mean, we've talked about it, but you're not going to see it. We have a few areas of technology that really matter to us that range from fundamentals all the way up to applications. We don't limit ourselves to any one of these. We have some expertise in MEMS and optics, and we need some expertise in RF. We you combine this into sensors, actuators, emitters, and the like. You start to build components. But in the application area of untethered UI and desktop UI and ubiquitous computing in general, we also have an interest there. We're not pigeonholed. We're not trying to say, oh, our interest is in MEMS and don't bother us about applications. We're trying to span that whole spectrum. And it's important that we span that whole spectrum, both top to bottom and left to right. So what are our projects? And the projects, this is pretty much an outline for the talk itself. Our projects range from displays to MEMS to what we call physical UI, devices used for UI, down into the systems for invisible computing. And you can tell I don't like the term wearables. In fact, I'm not even sure wearables shows up on your screen. The very last line says wearable technology. It's just that wearables have a bad name in a lot of places. We're talking about wearables that non-geek wear type of stuff that actually make the personal kind of technology that you would carry around with you. So let's start looking at displays. This is a display that Gary built I thought you built this 2 years ago.
Well, 2 or 3.
Okay, 2 or 3 years ago. This was a question of what would you really want on your desktop, and the knee-jerk answer is more real estate. Nobody has ever asked for less real estate on their desktop, especially if it's flat and doesn't take up a huge amount of the depth of your desktop. So Gary built this rear projection experiment, and it was shown at TechFest and was used in a lot of UI experiments. And in fact, if you look down at the bottom here at the publication that George and Desney and Mary put together, what they found was that there is a real productivity increase in certain areas. Without revamping the operating system, without revamping a lot of anything, there are real productivity increases to be had from large displays, and that's incentive enough to investigate this area. Now, the other incentive for investigating this is the less scientific approach, and that is you build one and people walk up to it and say, gosh, I really want one of those. And that is the universal reaction. So even though we can't quantify that, we know that there is a demand for that. Again, a reason for studying that area. I'm going to skim through this, if you don't mind, Gary. The fact is that big displays are good, and a bigger display would be better. I'm summarizing very, very rapidly what these slides say. Now, this is the bigger, better display. This is the D-Sharp display that was shown at TechFest and on CNN and at executive retreats, and this has gotten a lot of attention for good reason. One, it's something you don't see every day. And if you don't see it, and it was never built in the first place, you can't sit there and imagine what you're going to do with it. By building it and putting it into the hands of people doing experiments, and by showing it off to people outside, then we get the reaction that says, oh, we didn't think of this, but we can sure think of what we'd want to do with it now. And putting it into the hands of those people is what we're attempting to do now. And we're getting good feedback, again, on usability in a quantitative sense, as well as the qualitative reaction of, gee, I could do something new and different with this. So that tells you right there, there is a reason to actually investigate the technology and build the demonstrations and get it into the hands of people that can write applications for this kind of novel hardware.
You talking about what drove the curvature?
It gives you a sense. There are a couple of reasons. One is it gives you a sense of immersion. If you'll notice, if you go back and look at the previous one, this is slightly curved, and the D-Sharp display is heavily curved. And the question is, what's the right curvature? What do people really want? Some people feel a little claustrophobic with that much curvature, and some people feel really tied in with the desktop environment with that type of curvature. There are some physical reasons for doing that too. One of them has to do with the angle of incidence. As you view it, you get the maximum use out of the surface area if you keep the angle of incidence as close to 90 degrees as you can. But that's totally a geek's argument. And when you sit down and try to experience this, you're probably not thinking in those terms. The real question is my data surrounding me, or is my data at a distance from me? And I'm sure there are other ways to evaluate the effectiveness of curvature. But it's big, and you know, flat and big may not be the way to go. This is again an experiment, something new to try. What's the real answer, Gary?
Well, I think the thing is that you want this to curve around you because it's the best form of reality. We now know this from various experiments done both in the military and by human interface technology people. You want to make the screen disappear. By having it look like a billboard, it does not.
Right. That's that sense of immersion that you get from this. Now, fine, we know big displays are great. Those are done with rear projection, which is not necessarily what we would recommend for mass production. We'd really like to have some sort of flat panel display in that form factor. None now exist. If you look at the current choices for technology, you'll see that you know, CRTs can go up to a certain size, and beyond a certain size, you have to get a building permit to put it inside your desk. That's a large piece of glass, and it weighs when I say weigh a ton, I'm not saying that figuratively. There are projection. You know, you can use front projection, and a lot of people do use front projection in their offices now. They're not getting any increase in resolution, but they are getting an increase in area. They're also being freed from their desk, and there's some merit in front projection, especially with newer, quieter projectors. But there's the problem of shadows and the fact that your email is now public display. There's some drawbacks to front projection. Rear projection's fine if you happen to have an extra room behind yours. And when we first moved into this building, we sort of felt like we did, and now we don't. Especially with interns here in the summer, we all know that floor space is at a premium. The fact is, there is no single technology that's going to give you, no single current technology that's going to give you big displays. So what's being proposed here by Mike and Gary and the rest of us is to tile a lot of small displays and build up big displays out of smaller tiles. There's some good arguments for that, regardless of what the technology is in the tiles. There is an economic argument for that. If you look at a cost curve, this, by the way, is not a real cost curve. This is for model purposes only. If you build I can build a display out of 3 LEDs. Somebody once asked me, how do you build a good real-time graphics system? And I said, you take a Cray 1. You can kind of tell when they asked me that question. So in 1979, when I asked this question, I said, you take a Cray 1, you put 3 light bulbs on top of it, 1 red, 1 green, 1 blue, and then you string out 512 by 512 Cray 1s. Notice that's less than VGA resolution. And then you fly over it with aerial photograph, somebody shooting down at it. And that's your ideal real-time display. You can do the same thing on a small scale today. Take 3 LEDs, put them together. You can now get blue LEDs that look pretty good. So you string these things out and build a big array of them. And that should work. And the cost of actually putting this together is going to dominate. That is, the material cost on the LEDs may not be that large, but the fabrication cost on the total arrangement is going to be huge. You could go to the other extreme. You could go over here and build a 10K by 10K flat panel, very large one. Estimates of the factory, that the cost of the factory to fabricate that comes somewhere around over the GNPs of all but about 3 countries, and the yield is questionable on anything like that. The sweet spot's in the middle. Build a bunch of displays at about 100 by 100 and just tile them together like bricks. We'll turn the fabrication process into bricklaying. And now your problem is one of just optics and mass production. We all know that mass production will get the cost down, way, way down. And then the ability to tile these together means that it becomes affordable for anybody who wants to build any configuration of display, small, large, or whatever.
Oh, you're going to address that?
Sorry?
You said it only becomes a problem with optics. You're going to address what the optics
Actually, there are three issues in here. If you're going to build it, you need a light source, you need an optic system, and you need a way of modulating the light beam. That's true of any display. That's not, no matter how you do this, you have to have those elements. So let's assume we have a light source and the optics and the MEMS shutters, which is what Mike and Gary are proposing right now. Then we'll end up with something like this. And the optics are cheap. They can be stamped. MEMS can be made very cheaply. And the light sources, I'm presuming, are LEDs in this case, but we're not tied to any one particular type of light source. And they can be made cheaply also. What's the unit cost for one module, Gary?
For the entire module?
Yeah, just an estimate of unit cost.
About $4 or $5.
In mass volumes?
Yes, that's right.
Okay, so you'll come out a whole lot cheaper. 10 by 10 of these is 10 by 10 array of these would cost you about the same as a 15-inch LCD today. But if you wanted to go 20 by 10, it scales just linearly as opposed to exponentially the way fabrication facilities do today. Much more economical for larger displays. And then the key after this is to tile them seamlessly, and that again is an optics problem. And I'll rather than getting into that, I'm just going to point at Gary and say, ask him. He'll tell you how to do it. It's not insurmountable. So this is a new approach. It's something that it's as much an economic model as it is a technological model. Sorry?
Can you go back 2 slides?
Sure. If I
The other one,
there.
yeah.
That one.
So when I look at the screen, what is the light I'm actually looking at? Where is it coming from?
Oh, you're at the far right.
Okay.
The light.
So it's whatever the shutter is setting out that
Yeah.
I'm seeing.
The shutters actually is modulating the light.
And see, what I'm trying to think is it's not a bunch of little light sources. It's actually one.
One great big. In fact, let's change this. Make this fluorescent. Make this polarizing optics. Make this liquid crystal. Make this polarizing optics. Is that familiar? Oh, and a dye layer somewhere. That's an LCD. Okay. Displays are a lot alike. Technologies basically have to have the same elements. This is nothing more than a shift in technology to some elements that might be cheaper than what we're using today. But the same elements are there.
And you control the shutter opening and closing.
It's no different than controlling the twist on the LCD. This is just a way of modulating how much light is going to go through. Choose the type of modulator you want. I'll show you some options later. Mike has several options. Any number of ways to do that. You can also fold this path internally.
But is there any reason why it should have a certain refresh rate or something like that? Can I leave one shutter on and light just keep coming, or?
That I'll show you a neat trick. You're asking the right questions. We'll get to that. In fact, let me, since you're asking those questions, let me very quickly run through one extra little piece of work and then get right into those issues. Display design is not the only thing we do. Display characterization is important. Here you see a fairly expensive piece of test equipment called a spectrophotometer, spectroradiometer.
Spectroradiometer.
The more expensive of the two.
That's correct.
Okay,
Yeah.
right. Spectroradiometer. Also, this will tell you everything there is to know about a display. Let me show you why this matters. Look at something that the company has put a lot of effort into. Notice that ClearType is by definition optimization of the display algorithm in response to the device characteristics, which means you have to know the device characteristics. We had a kind of interesting issue with a Sharp display where we optimized for the device characteristics as reported to us by the manufacturer, and ClearType didn't work, which upset a lot of people, on both sides of the Pacific. Gary went back into the lab, measured that particular device, found out that this gamma curve was very different from what the manufacturer told us. we gave the new numbers to the algorithms guys, who then reprogrammed the ClearType implementation and got a pretty darn good response out of a fairly cheap display, and made a lot of people happy. You can't trust what people tell you. You have to go back to ground truth. Again, looking at the hardware, picking the hardware to pieces, getting into the internals of the hardware, that's what we do. That's part of our job. We were very lucky. There's other things that people don't realize about currently available display devices. Until you measure it, you might assume that the gamut of the display is constant across all brightness levels. It's not. Here you see what happens to the gamut migrates to a smaller region as the brightness increases or decreases.
This is actually, I think, with angle. This is with angle.
Oh, I'm sorry, with angle.
Yeah, right.
This is not the brightness variation,
Right,
it's the angle
right.
variation. Right, the gamut shifts as a function of angle on these. It's something that we have no way of compensating for, by the way. We don't track the viewing angle, but we just, it's an unsolved problem as to how to optimally compensate for a wider range of viewing angle. But at least we know that there is this variation that has to be dealt with. It's very valuable to be able to get at the ground truth on that. Now I want to go back to Anandan's questions.
Right. Portrait display devices are becoming more and more fashionable these days. How does ClearType deal?
So the question is how does ClearType deal with portrait mode displays where the stripes in the LCD pattern become horizontal instead of vertical? You can still use it. It doesn't give you quite the benefit that you would expect on Roman text, which is dominated by vertical stripes. But you can still use it, and you still get some increase in apparent resolution. And it looks a lot better if you anti-alias than if you don't anti-alias. And one of the benefits of ClearType has been to focus attention on the quality of the anti-aliasing, not just on the displacement of the filters. So I'll give you a quick answer. If you have an option of turning ClearType on or off in a portrait mode display, turn it on. Even for the rotatable stuff, although it may be different tuning. There is tuning available. The tablet people have a different set of parameters to use in that mode. Now, whether they account for being able to rotate dynamically, I don't know. You'll have to talk to them. Okay, so this is phase 2. I'm trying to transition from the display devices into the mechanisms that can be used in display devices. MEMS are not just for display devices. They found a tremendous amount of application in display devices in their early use, but there are all kinds of ways to use it. This is a basic technology. It's a lot like, when transistors came out, people didn't say, oh, this is all about radios, or this is all about hi-fi, or this is all about missile guidance units. Transistors are basic technology. That's the way you actually build electronics, is out of transistors. Well, if you look at the boundary between electronics and mechanics, if you look at sensors, this is the way you do it. It's a fundamental technology. Displays is one area that we're interested in applying it, but there are lots of other areas. If you look at all the various applications of MEMS, not by us, but by the industry, in terms of volume, accelerometers for airbag activation are probably the biggest market for MEMS right now. But there are any number of other transducer applications that they can be applied to. Display applications you know about, and we're going to talk more about. Mass storage is something that's just becoming interesting. The densities available with a MEMS with the technologies that can be sensed with MEMS are very, very high. Being able to read in parallel, one of the beauties of MEMS is that anything you can build in parallel. Being able to read in parallel means you have a tremendous bandwidth you're getting.
You have the display mirrors toggling at 100 kilohertz. Now, who has eyeballs that can detect that? Why don't they run it at 100 hertz?
Because TI in using these things is using dwell time modulation, and you need to go, the speed of the device times the frame rate is going to give you the number of bits of resolution in theory. You do need that fast response. So how do you actually build these things? Well, the straightforward way is something called bulk micromachining, which is real simple. You take bulk silicon, you put photoresist on top of it, which doesn't show up on this projector probably very well. It shows up better. Look to your right. That projector is better. Probably. I have no idea what the technology used in projectors are, but let's don't get into that right now. You put the photoresist on top of it. You pattern the photoresist, and then you expose. And then when you get through processing the photoresist, you have gaps in it, and then you put this in hydrogen fluoride, and one way of doing it is stick it in the hydrogen fluoride and let it etch inward, and that's a lousy thing to do because you get all kinds of distortions of the walls of your of the features. The other thing you can do is just put it in a plasma full of accelerated electrons and beat it to death with high-speed electrons. And there you can get very precise, parallel, high-aspect features. It's an expensive process and one that is not readily available. But this is the kind of machining that you do in a silicon substrate if you wanted to poke holes through the substrate, which we occasionally do for flow meters and things like that. Now, there's another way of doing this, which is a little closer to the standard type of silicon processing that we're used to. Keep that example in the upper right in mind and think in terms of this region right around the hub, because we're going to go through some detail on the steps that are necessary to build this. So, number one, you start with a silicon wafer. This is standard, monocrystalline silicon that you use for any kind of IC fabrication. In fact, the steps we're talking about are precisely IC fabrication steps. It's just we're going to do some funny stuff in the middle. So the first thing you do is you put on an oxide layer. Again, you just sit there and diffuse, turn up the heat, put in a little bit of gas, let it diffuse in for a while, build up this first oxide layer, take it out. You can etch that oxide layer, same old lithography steps that you would use anywhere. Again, this projector is showing it and this projector isn't. Next step, go in and deposit polysilicon. This is not the monocrystalline substrate. This is a standard amorphous silicon layer on top. You deposit that. Notice that the deposition is conformal, that it doesn't exactly give you a layer that goes straight across. It actually dips down into the holes that you created in the previous step. You can etch that. Again, same type of photo etching that we do in standard CMOS processing. Next step, go in for second oxide layer. Since this is the fusion process, Mike will have to explain to me as well as you why it's conformal. But assume for the minute that it is, and again, you might not care, so we'll just gloss over that and go to the next step where we etch through all the way to the bottom, which is legal in this process, I think. Okay. There are rules you have to follow, by the way. If you're really clever, you can break the rules. Mike breaks the rules. Last thing you do, well, not last thing you do. Next thing you do is lay down another layer of polysilicon. This again is conformal, and you can see it really gets down into that. It goes all the way down to the base silicon layer to form a post. Etch away. Now, what you end up with is a bunch of layers of oxide and polysilicon, just like you would in any CMOS process. And the last step is something called release, where you go in with hydrofluoric acid and etch away the sacrificial layer of oxide that you laid down. And what you're left with, you use polysilicon as the sacrificial layer. You etch that away. What you're left with are the oxide layers, first and second. Silicon oxide glass that is a good structural material. In fact, as you can see, it does a pretty fair job of building wheels and gears and axles, just as you see above. That's exactly the steps that were gone through to build that wheel that you're looking at. What's the size of the wheel? What's the diameter on the wheel? 200 microns.
Is the wheel the red layer?
The wheel is the red layer, yes. Okay, let me back up a second. The process we don't do this in-house. We sit down, or Mike sits down at a CAD station, generates the design, emails it to a place called Kronos, which is a division of JDS Uniphase. They go into an obsolete CMOS line, which isn't much good for anything except MEMS. And they will build him a 1 centimeter by 1 centimeter plate pin. It's like you have this much real estate, you can put any kind of amusement park rides you want in that 1 centimeter by 1 centimeter piece of silicon. They will go through and give it back to you either released or unreleased, and most of what we've gotten back has been released, but it is not mounted on any kind of header. It's just a little bitty chip of silicon that comes back, and Mike puts it into a probe station and starts exercising it. That's the process we go through. It takes 6 weeks, which is kind of frustrating. If you were writing software and it took 6 weeks to compile, you'd be really upset. Nevertheless, there are a great variety of things that can be done here. Most of the research that Mike has done so far has been on novel low-voltage actuators. We're very much a low-power portable. We have a low-power and portable frame of mind in our group. So whereas a lot of stuff you see in the industry is electrostatic, high voltage, ours is low voltage. Yes?
Are you by any chance trying to show us the video?
Okay. So if you can look on...
No.
Okay. Alt F7?
Or whatever it is you toggle your laptop display toggle. If you can blind your display, we'll see the video.
Let me blank my display so you can see the video. I'll be darned. Rick gets the door prize for today. That's been driving me crazy ever since I set up. This is the video. Did you miss the other videos? Never. Okay. This is a thermal actuator. You notice there are a bunch of these ganged together. You gang them together, you get more force than you'd get out of any single one of them. And the 2 kilohertz response is, you look at it and you say, how in the world will I get something mechanical to run that fast? And the answer is, it's tiny. It's really tiny. Now, some of the principles behind this, let's look at how you build that kind of buckle beam actuator. It's real simple. You build a thin layer of polysilicon in this case. It has to be a conductor. Silicon dioxide, any of the oxides are not conductors. Polysilicon is a pretty good conductor. Not as good as the gold that's layered on top of it, but still a good conductor. Run a current through it, and what happens is you heated it up and it expanded, and it doesn't have anywhere to go since it's anchored on the end, so it buckles. And you get that displacement, and that's what you use as your force. You gang lots of those together, and that's how you get the kind of force you need to move mirrors around. There are other things you can do. If you're going to extract force from this, extract it off the point of maximum deflection, or in this case, Mike wants to get torque out of it, so you want the maximum slope to extract torque. And that point occurs as at about 1/4 of the way in from the end. And at the point you want to extract the torque, you put a lever. And if you put a mirror at the end of that lever, then you begin to get the idea of how either that or it's a set of oars for a galley for ants. Your choice of how to use it. But the point is to extract torque out of that heating. Now, if you put some enhancements in there, you can get even more. You can do even better. enhancement number 1 is to put a spacer, that is a bump in this thing. That'll deflect it even more out of the plane. And as you saw in the fabrication explanation, you can get bumps real easily just by, it's sort of like when you make a bed, if you put a pea underneath it, you'll see a little bump on the surface. Just using fairy tale analogies here. That's what you do here, but it gets exaggerated. And using that gives you the asymmetry that's necessary. Now, the other thing you can do is curl it even further out by using what's normally a detrimental effect, and that is that if all of these layers, including a gold layer on top, are being held in place by the sacrificial layer, everything's flat. The minute you etch away the sacrificial layer, any residual stress in those materials will be released. And in this case, residual stresses are pretty large, and you've got two dissimilar materials, so the residual stresses are going to bend, and that's exactly what happens in this case, and you get even more deflection out of the plane. So that's the kind of trick. These are a combination of tricks to get the mirror really far out of the plane of the substrate. I think right. Now, how do you build any kind of deflection, the mirror deflection system out of this? Well, as we saw before, you want to gang several of these, and just to get into the labels on which is which, I'm going to just put them all up there at once. Sorry. Quick explanation. Since you guys have had the benefit of the superior display down here, I'll give the explanation over here, just to even things out. Here's an anchor point. Here is that point of maximum slope. We've ganged together an axle, so to speak. It then goes to a lever and lifts that edge of the mirror. Same thing happens over here. It lifts this edge of the mirror. This is the axis of rotation. It's held down, clamped to the substrate. So now you've got an X control and a Y control. You pass a current through here, and you heat this up, and it bends that way. You do the same thing over here. It heats up, it bends that way. That way. And you do that in combination. You've got X, Y control over the deflection, and you can do the following. Here it is in action. As you can see from the label, that 0.2 of a millimeter reference, and the mirror is considerably smaller than that. Down at the bottom, you shine a laser on the mirror. This is moving really fast, a lot faster than you see in the movie. You shine a laser on the mirror and deflect it onto a display screen, and what you end up with is a MEMS line drawing display. A very, very small line drawing projector that runs off of low voltage. Not necessarily low power, but low voltage. Something that you could put into a light pen. It's my favorite application. Okay, go back to the iMods. How are we going to? You were asking about the modulators on the iMods. So here's an idea. If you go in and use that residual stress to curl a mirror up out of the display and integrate that in with the optics we showed. Now, this is not quite the same. This is not pass-through optics. This is folded. We'll take that original diagram, fold it, and use reflective optics. And as you can see, let me just jump straight to the animation. You can see as the deflection changes that you're going to turn the beam on and off through a certain region. Did it show up over there? Good. If you missed it, we'll show it later over here. This is a prototype a recent prototype. It works fine. It's not fast enough for the types of displays we want to do. There is something else pretty nifty in this, and I don't think we've exploited that nearly to the full extent, and that is to take advantage of mechanical hysteresis. Who was asking about storage so you don't have to move this as fast? Yeah. This has there is hysteresis in this process, mechanical hysteresis. That means that you could bend it and it stays sort of bent. and then you bend it back and it stays flat. And I like to think of that as the beginnings of a mechanical frame buffer. Something we wouldn't normally think about in our electrocentric viewpoint. But, you know, the mechanism's there. The physical mechanisms are available. When you're doing this kind of research, you run across that kind of thing, and it starts starts your thinking to spin off into this different direction. That, I think, is a really, I don't know how to use it yet, but I think it's a really nifty effect.
The one argument against this kind of mechanical, you know, things is their wear and tear over time and so on. What's the situation in the MEMS case about this?
Some of the devices that you've seen wear pretty rapidly. Anything, the gears, motors, etc. They wear pretty rapidly. Some of these have very long lifetimes, and we don't know how long they are. If we may have an idea, but we don't know for certain. Tom?
Can you build a microprocessor out of the exact same technology? I mean, can I put a microprocessor, 1 micron or 5 microns over?
Good question. Can I build a microprocessor in the same technology? And let me filter your answer rather heavily and give you the answer I want to give you. And that is that it's entirely possible. This is a standard silicon process. The one we're using is not a state-of-the-art 0.13 micron process, and it doesn't have the same process steps. When people want to do exactly what you're talking about, they will do the following. They will build up a standard microprocessor circuit, and they'll put one additional metal layer on top with a sacrificial layer underneath it, and they'll go in and pattern the top metal layer, which allows you to put in resonators and a few other simple things. In fact, maybe this may actually qualify as the kind of thing you could put in the top couple of layers. And then they go out and etch that separately as a post-process. So what they did was they took a standard CMOS process, got all of their circuitry into it, left the top unpatterned, went into a second process, patterned that for the mechanical devices, and now you've got the mechanical devices and the electronics integrated completely together on the same substrate. A few extra process steps. There are some limitations on what you can do, and there are continuing limitations. In particular, that post-process has some temperature limitations. You do not want to exceed certain temperatures for fear of destroying the circuit you just built. But the simple answer to your question, yes. Okay, moving along to, I'm going to glide through this pretty fast. That's the sexy part, you know. That's using all the fancy microelectronics for sensors. There are some somewhat less exotic processes that we can use. My favorite is a spray can full of conductive paint. I can spray that on almost any man-made surface and create a capacitor, which then can be used as a sensor. And some work by Ken Hinckley and Mike on doing exactly that with a mouse allows you to detect when your hand is in proximity, not just when the mouse is moving or when the button is clicked. It tells you when your hand is near, when your hand is touching, when your finger is on a button or near a button. And the UI that is available to you with that additional sensing is considerably richer than what you get with just position and mouse clicks. And it's cheap. It's extremely cheap to do this kind of thing. So some of the examples that have come out of the lab have been capacitive touch slider, same principle that Mike has been working on. It's extraordinarily inexpensive to embed that in almost any piece of plastic you can think of, whether it's a tabletop or the side of your PDA. The IR range sensor is a way of getting 3D input with very inexpensive emitters and sensors. The putting the accelerometers inside of the iPack allows you to use tilt as an input, something that Ken and Mike and Eric and one of the interns published in a Chi paper. And then Victor Ball and Eugene Shi, who is a former intern in this group, built the brick that goes on top of the iPad, mainly for communications extensions. All of these types of things are the type of inexpensive and more conventional extensions that give us the richer UI that we're trying to get out of our experiments. So what if we extend this completely off the desktop and completely out of, away from these display-centered devices into just people? There's a big difference between a person standing in front of the display, and I don't care if it's a wall-size display or a desktop display or a handheld display, and a person just wandering around. A person just wandering around is of great interest because that person may or may not be busy, that person may or may not be in touch with people they need to be in touch with. There are all kinds of reasons for knowing what that person's doing and what their state is. We want to provide, this is a corporate commitment. We want to provide services and connection with other people anytime, anywhere, no matter what. Your stuff is available to you no matter where you are. That's a principle. How do we make that happen? Down at the very lowest level. Forget the software infrastructure. Well, don't forget the software infrastructure. That's how we make money. But in addition to the software infrastructure required to do this, we ought to pay attention to the low-level details of how it's implemented. And again, that's what our invisible computing effort is oriented towards. Now, there is one thing that drives everything we do in this space, and that is because every single device is portable, every single device is small. Their power is the issue. Top three. If we have a list of the top 5 issues, power are the first 3. This happens to, I love this. I just opened the drawer at my home. This is my wife's battery drawer. I think we're pretty much an equal opportunity purchaser of batteries. There's everything known to man inside of that drawer. And we are constantly using, pulling out old ones and plugging in new ones. That's just a fact of modern life. When you look at the portable device designs that go on in this company, the question of how long will this last? Will this last a day? Will this last a week? Will this last a month without recharging? Those guide designs more than any other single principle. Here are the math behind it. For those of you who don't know, this is about as simple as it gets. Power equals effective capacitance times the square of the voltage times the frequency of the clocks in the circuits. And this tells you why people have gone to lower and lower and lower voltages in digital circuits, because that's square term. Big wins to be had from that. Now, you can get, the nice thing about, if you decompose Moore's law into its components, you'll find things like shrinkage of feature size of 13% per year, which translates into an increase in frequency of 13% per year. And that means that for a given size circuit, we can run it that much faster and get that much more computation out of it. Take the same argument and apply it to the area of the circuit. If you want to get the same amount of computation out of this block of silicon, you can shrink it by 30% per year, or 25 if you do the math a little more rigorously. But 25 or 30% per year. The same functionality shrinks year by year by year. It gets smaller and smaller. Oh, by the way, if you're only interested in doing the same amount of work, shrink the battery voltage, shrink the effective capacitance, and let the frequency grow up, or let the frequency stay constant. Your power needs are shrinking too. That's what Moore's law gives you. This is not the way Moore's law is presented to you in public. Moore's law says that if you really want to push the envelope, you can double your speed every 18 months, and then power ends up going up a little faster than that. This is the Moore's law side for small devices, small battery-powered devices. There's a real win to be had there, and that's one of the things that we want to take advantage of. There are other things we can do, too, and that is managed duty cycle, which is just a constant term in front of that whole right-hand side of the expression, and that's something that we'd like to do. And that is an algorithmic exercise. Again, something that enters into our design. When I keep talking about no geekware, the vision is to embed these devices into everyday form factors. If you're used to wearing something on your belt, put more circuitry into it. If you're used to wearing shoes, put circuitry into it. If you don't wear shoes, there's certain services that are not going to be available to you. That's not just restaurant service either. It's right. No, yeah.
Can we wear shoes at the airport?
Well, that's a good. Let's don't get into that. Right. This does run counter. This whole argument runs counter to certain trends. This is an old slide, and I haven't updated it for the past year. So, but yeah, that's a good point. If I have tiny little wires and a lot of piezoelectric film in my shoes, chances are I probably won't get on a plane. That's no reason for us to stop doing research in this area, though. The fact is, we're looking for small modifications to everyday devices to do the work we're doing. Our first experiments in this area had to do with just sensing what the user was doing. Very, very simple. Put accelerometers in the shoes and have a little wireless hub. Now, a lot of us wear wireless hubs routinely. Some of us carry our wireless hubs in our pocket. Some of us wear it on our belt. If you keep it in your purse, that's a problem. Because if you want to communicate from your shoe to your wireless hub, you need some kind of communications path. For this experiment, we initially used wire, but we eventually started using electrostatic coupling. We have had very little success with that. That's a very difficult problem because people tend to reconfigure themselves. We asked the question, is somebody going to stand like this when they're trying to communicate to a server? Because they know this is a good configuration for communicating to a server. And we say, no, it's absolutely insane. And I say, well, yeah, but you go talk to my wife. She will tell you the maximum signal strength in every airport on the East Coast for her wireless phones. We're already used to doing this to a certain extent. I don't anticipate that we would go down that trend so that people, do funny things in public in order to... Sorry? People do this in... I know. Look, I don't want to... We consider that not terribly silly. Some of us consider... Let's don't get into it. There will be a talk at some future time about the social issues here. We're talking strictly about the electronics. We have looked more at sensor signal processing. We've looked at that with more success, mainly because it's a simpler problem. Let me give you an example, jumping ahead to the signals in question. If I'm walking around and I have a heel-mounted accelerometer, I could take that signal and transmit it back to a server. And in fact, I could filter it to below, say, 30 hertz and not lose any of the information. It's a very low-frequency signal. I don't need Bluetooth for this, by the way. This is a really low-frequency signal. Or I could do something more clever yet. The question is, do I need that entire signal to tell the server what I'm doing? If I'm walking, I can take the peak amplitude, if you see in the top right trace, and I can put a timestamp on each one of those, and then I can go back into a classifier and say, here's the peak amplitude and along one axis, and I can say, and here is the period along the other axis, and I can build a classifier that tells me approximately what that person is doing, and without sending the entire signal back. On the other hand, if I want to uniquely identify the person walking based on their gait, which some researchers have done, then I need to send the whole signal back. To send the whole signal back, even though it has a narrow bandwidth, is going to require more energy than if I just send these extracted data. A lot of the problems that we are trying to solve in the ubiquitous computing area have to do with trade-offs between local processing and remote processing, power and bandwidth, balancing them together. It's a partition that gives us the optimum use of these devices. That is a difficult problem, and it's something that we are trying to look at. In the end, roll all these technologies together. What do you end up with? We claim that it's not the geekware that some people think that we'll get. Although people wear headphones in public, people wear earpieces in public, and maybe that will be what people do to have all their sensors. They will be wired. The clothing styles they'll have fake wires to make it look like you got more expensive pants. All of that will happen, I'm sure, but we're not counting on it. The real key is that if we're successful, you walk around, nobody knows that you're any different. Nobody knows that you're any smarter. Nobody knows that you're any better connected. You look just the same. This stuff that we're talking about is invisible. It gets woven into your everyday life, and you don't outwardly show any of the stuff that we've been talking about. If we do it right. Now, I know you didn't come here. Let's gloss over. We have lots of partners. We have lots of goals. We have lots of directions, and we're desperately looking for somebody that knows RF better than any of us know, which is the most important point if we look at the directions we want to go in. But that isn't why. I'm sure it's not why any of you came to hear this talk. What you really want to hear is what's inside that lab down the hall. So here's a lab tour. This is a little UI challenge. Which one is the, we'll go first, bottom one, right, the shop. Okay.
This one's
Now,
fine. You can switch back and look at
sorry?
it. This one was viewing fine. You can switch back if it's easier for you. You can see this even when you can see the screen.
We'll give it a try. That was actually... now we can both look at it. Okay. Principle number one of doing this kind of research. If you have an idea, you better be able to implement that idea in a hurry, because if you can't, you're going to get slowed down and you're going to get hung up on ideas that aren't going to pan out. It's okay to pursue an idea that doesn't pan out as long as you don't spend much time on it. As a consequence, we have a fully equipped machine shop. You have an idea at lunch, you can have it instantiated by 5 o'clock. Just go back to the machine shop and start grinding. Including the machine shop is the the CNC lathe, a nice piece of equipment that you better not get close to without talking to Mike. A bandsaw, which is quite capable. We also have a big rock on the floor that we don't know what to do with, but if you ever need a heavy piece of granite, we have that too. We have, when I put this in the budget, you see over here this 3-axis milling machine, a very precise milling machine. It was entered into our budget as a matter compiler. My boss doesn't read science fiction. His boss doesn't read science fiction, but the senior VP of research reads a lot of science fiction. And when it got to his desk, there was a question raised. But it really is a matter compiler. It will make whatever you want to make. Go into a CAD tool and just start grinding, and it is a really nifty thing to have.
I've seen there's these laser deposition things that basically out of powdered metal and a laser basically build up
right.
3D a metal form. Do you have anything like that?
The centered stuff. The one that not this year, right? Next year this year we're getting the laser cutter, which basically is the interface into the laser cutter is basically printf, which means that anybody can start using the laser cutter. But in terms of the centering and the building up of the 3D structures, we don't have that in the budget quite yet. But it's the right idea, and that is that it really is a matter compiler. It builds whatever you want. If you want to prototype something, it'll build it very, very easily without much skill on the part of any of me. I have no skills at all, and I want to be able to use this. And that's why it's all numerically controlled. There's some more mundane things, equally useful, a shear, a brake, one heck of a drill press. Again, we're building small devices. In order to hold tolerances, you have to have big machinery. That's the paradox of this kind of lab. But it's well equipped, very well equipped, and that's how we get work done. So let's switch over and look at the outer parts of the lab. First, I'm going to go over on Mike's side of things. We talked about the MEMS devices. Let me swing around and look over here. There are a couple of things that, when a device comes in, Mike puts it on the probe station. You can see right here. And that's an XY positioning table. It has a vacuum that holds the chip down in place. And he can take very fine tip wire and put it onto the pads. This is an unbonded circuit. Put it on the pads and apply voltages to it, look through the microscope, and decide whether the machine is doing what it should do or not. Should he want to integrate this into something that he can carry outside the lab, then back here in the corner is a wire bonder. And if you're sufficiently patient and have sufficiently sufficiently skillful, you can do wire bonding to a header and then go plug that into a standard IC socket. But 9/10 of what has to be done can be done on the probe station, because it's a question of design, test, verify the design, and that can be done in this experimental setup. This is Mike's. It says UI devices. That's Mike's bench. Don't touch it. It's his. By the same token, don't touch this one. It's mine. And this bench over here has a really nice oscilloscope. You can cut and paste from this oscilloscope into Excel. That's something I couldn't do back when I was in college. Very, very nifty if you're going to write up whatever it is you're doing. It'll also do Fourier transforms internally, but so will Excel, so it's not a big deal. To the left of it is a real hot spectrum analyzer, which I haven't seen for the last year because the Zenith people are running all over the country with it, but we're happy to be of service to a product group. We would like it back if any of you guys are here. Yes,
couple years.
Yeah. Ray, what's Zenith? Is the question?
Oh, what's
Smart
Zenith?
personal objects, is that?
Yeah, smart personal objects, incarnations of those wearable computers that you're talking about.
Honest to God products from people that you got two groups here. You got me, who can talk about this stuff, and you got Ray, who can actually make it happen and sell it. So there really is a hardware products group that deals with tiny little devices. Okay, that's the kind of the electronic side of things. And if you go over to the other side of the bench, this begins to look like, that looks a lot like an optical bench, which it is. This is Gary's side of the lab, which is easily identified by the V8 with 2 4-barrel carburetors, or is that 3 2s? I can't decide which. Optical bench is a wonderful playpen. Again, it's the same principle. You got an idea, go breadboard it on the optical bench. 90% of what I showed you has a light source, some optics, a modulator, and a sheet at the other end, and wax paper sometimes works very well for that, but a sheet at the other end for a viewing service with any number of combinations. And that's what this is. This is better called the any number of combinations bench. Try it out, see how it works. And there have been some bizarre things done on that bench, some of which were very promising. Here's more optics over here. A small laser printer museum on this shelf right here. This is Ken Hinckley's bench. A lot of the work you saw with PDAs is Ken's work. Go back in the corner. This is the CAD station. If you're gonna generate a MEMS project, you do it here. If you're going to generate something for the numerically controlled milling machine, you do it there, and it comes out back in the back. This is a fairly old photograph. Notice the floor's clean. There's not stacks of books. If you walk in right now, you'll find that people actually do real work there, and it shows. Anyway, that's the place we work. It's a wonderful environment for it. We do a lot of fun stuff, and we hope it has some impact. More questions?
So on the spectrum from sort of pure research to shipping products, and they're impacting products going to ship the next year or two, Where do you guys sit? Where do you want to sit with your charter?
That's an excellent question because our management asks us that all the time. My answer to that is real clear. Where do we want to be in the spectrum between pure research and a product? We want to be at two spots. We want to be far over on the speculative side, on the pure research, and we want to be somewhere just ahead of the product groups, so that we can be of use and so that we can feed that process. Not that we know what the product groups are going to want to do, but we need to be in that space so that we can work with product groups. I think the display work that you saw, the D-sharp example, is a really good one because that's something that product groups can get useful work done on. They can learn a lot from that. iMods, on the other hand, is a little further out. So this is not. We don't want to accomplish these two goals at one point in the spectrum. We really recognize that we have to have multiple projects going on to hit those two spots in the spectrum. Same thing's true with the MEMS. Same thing's true with the small devices. Other questions? Well, thank you very much for coming. I hope you enjoyed it.